Okay, hello everyone. Thank you for coming to the second lecture of the Machine Learning Fortnight. And today we will be talking about how to use natural language processing in recommendation systems, basically. And moreover, we're going to cover a few more stuff, such as, well, how do you compete on Kaggle? How do you prepare yourself on Kaggle? So how do you set up your environment and everything? I'm also going to give some tips on the competition, and we're going to go through the notebook that I prepared for today. So from the theory, there won't be much new stuff, but rather we will actually go through the implementations, because I think this is what the majority of the people are actually struggling with in the competition themselves. Could you please raise your hand if you're actually participating in the competition? Okay. You are?
I'm not sure.
You're not sure? I mean, you can still just join the competition, see if it works. If it works, then cool. Because, as you can see, we don't have actually a lot of people participating, and the top 3 teams will get the prizes. So if you just make a submission right now, you're gonna win, even if it's like the 0 score. So I don't know about you, but I would actually submit something. Even the sample submission file, because that's already like some score. All right? Okay, so first of all, let's go through Kaggle and actually figure out like the whole process of what is it in here. So if you've actually joined the competition, you probably should have gotten an email, which is something like, it's actually my student email. So if you actually join the competition, then you will get an email with a link like this. So it will redirect you to the competition itself and allow you to join the competition. And of course, for that, you will need a Kaggle account. Why is it not working? Okay, let's imagine it worked. And basically, it will redirect you to this page where it will ask you to participate in the competition. This is the description of the problem itself, the evaluation, and how you have to structure your submission file. It has a little tutorial, but let's just not go there. So first of all, to start, you have a data place. So you have a few data files here. So you have the train file, which is 1.3 gigabytes, the test file, the sample submissions, and game metadata. Game metadata tells you about what the games are, so their IDs, their names, and different other parameters. The train data set is similar to the test set. You'll have pairs of Steam IDs and app IDs, which is like the user ID basically, and the ID of the game. And then from that, you have to predict if the user voted up or not. Voted up means, well, if it's 1, then the user actually voted up, so he says that he likes the game. If it's 0, then that's false, meaning that the user did not like the game, so thumbs down basically. And the rest of the parameters are just supplementary, so you can use them somehow if you figure out how to use them. But we will not go through that in the lecture itself. So for example, how do you submit? Well, you can just download the sample submission file, open the app, unzip it. See, we have it in the documents. So you have submit predictions. You select the file, and you go into, you just select the sample submission, open it. Sample submission, submit it, and hopefully that works. Indeed, it does work. It is evaluating the submission right now, and then it will tell our score, which technically should be the same as in the leaderboard. Yes. Okay. So now in the leaderboard, well, I don't appear because I'm a host. You cannot see me there, but you would be placed like in this top 2, for example, because, well, sample submission is better than the last team so far. So that's something they can do and basically already win the competition. If you want to do more, you can actually program some stuff by downloading the data and following some steps. There are also training shards, which is basically the same training set, which is train.csv, but is broken down into 10 files. And that is done because some of the participants have bad computers which cannot actually load the files. So if you want to use the training shards, that's also fine. If you want to use the train.csv, that works for me personally. So yeah, do whatever works for you, basically. Yeah, any questions about the competition itself? If you have any problems, you can also just ask me later, and yeah, I can help you with the competition or understand something, or yeah. So yeah, this is about the competition. Yesterday, on the last lecture, we've talked about introduction to recommendation systems. So it was a quick lecture, 30 minutes, just discussing what recommendation systems are. As you may know, there are, well, content-based recommendation systems, and then also collaborative filtering. And we're gonna go through them together again. So if you wanna follow me in the tutorial right now, what you'll have to do is you'll have to open the notebook on the website. So it will be available, yeah, as we cover ml Fortnight, svcover.nl. If you open this website, it will redirect you here, which has the notebook of the second week or the second lecture. And if you open that, that redirects you to the Google Colab, where it has a similar code that I have right now running on my notebook, and you can also just follow me, or you can run it on your own time whenever you feel so. So today we're gonna be walking through the anime recommendation database. It's a very huge collection of animes, and personally I've worked with it before already, and I had a few models made myself, and today we're gonna try to beat them. But yeah, so basically what this data set is, you have similarly animes, and you have ratings. Actually, this is the one. You have an anime list of ratings. So you have the user IDs, you have anime IDs, and you have the rating that the person gave it. And yeah, that's what we can see here. And also you have an anime with synopsis file. So it basically has the anime ID and then like, what is the ID, the anime about, basically. So that's what we're gonna go through today. And that will also explain you how to actually use, well, the description of an anime inside the project. So I'm gonna run it on my local computer. If you wanna run it, then you're just gonna have to use Google Colab. So can you see this? I think this should be good. Right? Okay, cool. Yeah, so first of all, we're gonna download the libraries that we have prepared. So we're gonna use PyTorch, transformers, and also the Kaggle API. I'm not gonna run this, or actually maybe I will. Oh, wait, no, I don't need to run this because I have the data already installed on my machine. Exactly. Cool. So yeah, you're gonna have to replace the username and the key with the Kaggle API. So you can just open settings on your Kaggle, and then create a new token, or just create a new token, and it will download the token with your username, and then you just replace it here, and the API should work when you run the cell. Next, we're going to import a few libraries. So we're going to use pandas, numpy, matplotlib, seaborn. That is for just standard data science. Pandas is to open files. NumPy is to work with like linear algebra, basically. Matplotlib is to draw plots. Seaborn is a fancy way to draw plots. And also, TechUDM to make progress bars and everything. And just scikit-learn by default, and TensorFlow. So when this is done, we're gonna open the first file, which is the ratings file. Let's load it. Basically, what the ratings file is, as we saw earlier, it's table of user IDs, animes, and ratings. And first of all, we're gonna just inspect the data and see how it is distributed. So the ratings seem to be distributed okay, like almost normal. So we're gonna divide it by 10 just so that they are normalized from 0 to 1, and easier to work with them. And we're gonna do our first range of data analysis. So first of all, we're gonna inspect actually the distribution of how many ratings each user has given. And well, it appears to be that some of the users gave more than 1,600,000 reviews, which is quite a lot, to be honest. And I did some math here. If you assume that the episode lasts, well, and a series lasts 12 episodes, and each episode is 24 minutes long, then if you multiply it around, you get that huge number of hours. And if you think about it, that's about 264 years of anime, non-stop. That's crazy. So probably that's not a human done. That is probably a bot that was parsing the website or putting down ratings. So of course we'll have to remove that. But how do we actually remove that? So let's make an approximation of how much is a reasonable anime weeb is going to watch anime. So let's assume it's around 10,000 hours of anime, which is about 1 year and 2 months of non-stop watching. That seems pretty good. Like if they're like 30 years old, that's quite doable. Like a few Narutos and One Piece and you're good. So yeah, this is approximately 2084 animes if you convert it back to anime scale. So probably like if anyone has more than that, that's a bot.
We're European, we're not American. You can stay in hours.
Yes, okay, sure. So first of all, yeah, we're gonna select the bots. How do we do that? Well, we look at the ratings and look at the user IDs and how many times they occurred, right? So it's value counts. That's gonna return us how many times each user has occurred in the ratings. So essentially it's gonna give us how many ratings each user gave. And as you can see, yeah, some of them are quite big. So what we're gonna do is select the ones that have the value count greater than 2084. So it's gonna give us true for all of them who have it greater and the false for none. And then what we're gonna do is basically take the index of this table for the values that have the value true. I think that makes sense. So essentially what it's going to give us, we're going to get the IDs of all the users that have their value greater than 2084. And then we're going to just filter out our ratings table. So we're going to remove all of the users that have their ID in the bot users list. And that is going to leave us with some people. And if you inspect the data set again, well, this is more reasonable because the majority of the people don't watch that much anime, but still it's doable. So we're going to leave that. And yeah, it's crazy how many people still watch anime. So now let's just think for a moment for like, how do we actually do game recommendations or video game recommendations or whatever? Well, for that we need quite a good amount of ratings for each item or from each user. So if our user is going to rate only like one anime, that is not enough to tell something about the user, right? Like, well, if you think about it, maybe, but I would say it's hard to tell. So you're going to need like a considerable amount of content that they had watched. And the same goes for anime. If the anime was not watched enough times, then probably we cannot tell anything about it. Maybe it's not popular enough for actually us to evaluate it. So what we're going to do is we're going to filter out all of the users which occur less than 40 times. And we're going to do the same thing for the anime. So if the anime occurs less than 40 times, we're going to also remove it. And then we're going to repeat that multiple times, because if there was an anime that some user watched and then we remove that user, then the anime rating is going to decrease. So we're going to remove this and continue doing it until we converge to some amount of ratings. And this is what my while loop does here. So yeah, we are filtering out and seeing if the size does not change, then we're going to break the loop. And this is going to basically mean that all of the users and all of the animes have at least 40 ratings, which is quite a good number. And as we can see, we have 5 million, right? Or 54 million. That's still big. So it's good enough for us to train. Next, what we're gonna do is we're gonna add a few columns to our anime ratings table, which is just encode each user and encode each anime into values from 0 to n, right? So that is gonna allow us later to put them into embeddings or just have like a map table. Yeah. So if you wanna inspect the ratings table right now, it looks something like this. So we have the user IDs, we have the anime IDs, ratings, and then the encoded user IDs and encoded anime ID. Okay, now let's look at the other file, which is the anime with synopsis. If we inspect it, we're gonna have a bunch of anime, a bunch of their names, their average ratings, the genres they have, and the synopsis. So the synopsis is just a description of the anime. Genres are, well, speak for themselves. And yes, so what we're gonna do is actually check if some of the anime don't have or do not occur in the anime with synopsis. And that is indeed the case for 1,000 of them. But majority of them are in there, so that's good. So what we're gonna do, first of all, is actually split out the genres in here. Because, well, we would like to have them as a vector that we can work with. So yeah, let's take the action, adventure, comedy, and so on, and actually make dummy variables. So that's going to be basically one hot encoded or something like that. So yeah, basically what I did is I make the dummy variables using the genres, which are split by the comma. And yeah, then we drop the genres column. And for prettiness, we're going to just refactor some of the column names so that they have, well, a standard snake case representation. And then, yeah, we're going to look at the data set again. So we have the anime IDs, naming, average, and then a bunch of numbers. So as we can see, for example, for Cowboy Bebop, we have, it is adventure, it is a comedy, it's a drama. Yeah, it's a sci-fi in space. So seems to work fine, seems to be legit. So yes, now we can finally move on to training and testing. And yes, so we're gonna take our data set, split it into a 20% split, 20-80% split. And we're also gonna stratify it using the user encoded IDs. And that is done so that like we have examples for all of the users, and so that later we can test like, oh, so if we have 80% of the user for training, we're gonna have 20% of the user for testing. Yes, so now that's done. We can also inspect the shapes of the data sets. So shapes, yeah, those are quite big. All right, so now we're gonna also make another helper function, which is the results table. So what it's gonna do is it's gonna save the name of the model that we used so far, and also the test, the result on the test set. So yeah, it is basically a pandas table, and then every time we want to add a result, we update the pandas table, as well as we're gonna display the sorted values in the results table. Okay, so yeah, first of all, let's begin with a few baselines. Yeah, that are a good starting point. So yeah. Who knows what the baseline is? It's basically a simple model that we're going to use as, okay, this is like the easiest model we can do, and yet it's going to work okay-ish. And then if we're going to try to improve upon from it. So the first and simplest baseline model we can do is, okay, what is the user going to rate this anime? Well, it's basically going to be the average user rating that the user gave. So, well, if the user gave only 10s, well, then we're also going to try to say that the user is going to give a 10 to this anime. Or we can do it from the side of animes. So if the average rating for this anime is like 8, then we're going to say that, oh, this user is probably going to also say that it's 8. And, well, on average, that's going to be pretty good. So that's what we're going to do, right? So we'll have two baselines. One is the user average. So basically, just when we're asked to rate some anime, we're going to give the average user rating. And the second baseline is the anime average. So we're going to give the average anime rating itself. Makes sense, right? Okay. So yeah, let's go over the implementation. I decided to make it like a class because, well, it's nice. So yeah, we're gonna define a few stuff. So for the average user, we're gonna make the user averages, so the average value that each user has, and then the global average. So the global average is gonna act as a fallback value if the user actually didn't rate anything, or I don't know, something doesn't work. We're gonna have a fallback value which is gonna be the global average of the animes. So yeah, when we're gonna fit the data set, so we're gonna give it the training set. We're just gonna take the mean of the target ratings, and that is gonna be our global average from the training set. And when we wanna calculate the user averages, well, that we're gonna do that by just grouping all of the users, all of the ratings by the user ID, then select the rating and take the mean of that. So yeah, let's just go through it. I think that's a useful pandas function overall. Use it quite often. So first of all, let's look at our training table. We have the user IDs, anime IDs, ratings, user encoding, and anime encoded. What does the group by function do? It groups all of the rows which have the same user encoded ID. Okay? Then we select the rating column. So it groups all of them, and now they're like in an iterator, let's say. And then we select the rating column. So that means that all of the ratings are just like in one place. Now we can take the mean of that. So we're going to take all of the means for all of the users. And what that is going to return to us is, well, we're going to have a table where on one side, on the index, we have the user encoded IDs, and on the other side, we're going to have the average rating that the user gave. Yes?
What exactly, what data structure is it before you apply the mean? Like a single entry in rating there?
You want to see what this looks like?
Yeah.
So that's going to be a
Series.
it's a group by, but technically we can restructure it, I think, by applying a list to it, or I think so, or apply list. Apply list, yes. Or, yeah, this is too slow, sorry. Yeah, this should be faster. Okay, yeah, I'm gonna draw it on the board here. So, is there no draw?
When you transform it to a list, to me at least it's clear.
Yeah, well, if you transform it into a list, then you have like a table of where index is the user ID, and then the list is gonna be like all of the ratings that the user has given.
Yeah.
Right?
Matrix.
Yeah. Rating, but the matrix is gonna be like not of the same sizes because all of the lists have different length.
Yeah.
And we're going to just take the mean of those lists. So for each user. So this is what we get. Okay. Yeah, so this is what we get, and we save it as user averages. So now, when we are actually asked to predict, well, we're just going to look at the user ID and then save the user average that the user has given, if it is available. If it is not available, then we're going to use the global average. And then we return that as our predictions. And yeah, here we instantiate our class. We train it on the training ratings. Then we evaluate it or get the predictions for the test ratings. And then see how well it does on the mean absolute error for the test set. So we're going to run it. We get the progress bar like this, which tells us how fast it's going to go. So around 20 seconds. And yes, with every model, the time is going to increase because the model is more complex. And the last one is going to run for 40 minutes. But we're not actually going to run it, but it works, I hope. Probably, yeah. Okay, nice. So the thing completed, and we get the mean absolute error for the test set 0.1. So basically, our model for user average rating fails at about 1 point to the left or 1 point to the right. Something like that. Cool. Let's do exactly the same thing, but with anime now. So we're going to group it by anime now. And now if we want to predict some user anime pair, we're just going to look at the anime and say this is the average score for the anime. All right? Yeah, so it does exactly the same thing. Also takes 20 seconds. Oh, okay, now it's done. So as we can see, our model for anime average rating is doing a little bit worse than the user average rating, which kind of makes sense. Because, well, for every user, they're probably going to give more or less similar ratings. So now, yes, let's try to do better. So we're going to do some collaborative filtering. That is something that we have done last week, but we're going to do it again. And we're going to do it, actually, the implementation in TensorFlow, because, well, that's cool. So first of all, let's do some notation. So basically, we're going to try to optimize this. So our hat is the rating that we predict for user item, right? So UI, those are user and item. Then the mu is going to be the average rating overall. And then the BU is going to be the bias for the user. So the user is going to have some bias, which is going to shift it to the left or to the right, because maybe on average the user gives lower or higher ratings. Same does for the item, because, well, maybe on average the item is worse or better. And we're going to compute the dot product of the user embedding and the item embedding. And that is going to return us also a scalar value, which is going to be, hopefully, some representation of the rating. Make sense? It's basically a linear model of user item ratings. So now also we're going to define the loss function. It's going to be a, how do you call it?
Mean squared error?
Yeah, mean squared error, exactly. Yeah, I didn't put the mean here, so it should be 1 over n.
Squared error.
Yeah, just squared error, but it should be let's do it 1 over n also. Yeah, that's better. So we have the mean squared error here, and also we have some regularization terms. So that is going to regularize our P and Q, and also the biases. And, well, that is done because these models tend to overfit really quickly, easily. And yes, so now let's define it in TensorFlow. Probably you're not familiar with classes in TensorFlow, but it's quite similar to PyTorch. But even if you're not familiar with that, I think it's self-explanatory. Yes, so first of all, we're going to have a few parameters. So for example, the number of users, numbers of items. This is going to help us instantiate the embeddings because, well, we have to know how many users and how many items there are and how many embeddings we should have to make. Then we're going to save the embedding dimension. Embedding dimension, well, it's how dense our embedding is. And then we are going to have also the L2 regularization parameter for the embedding and the L2 regularization parameter for the bias. And I read a few papers, and it is recommended to have the L2 for embeddings higher than the L2 for bias. Apparently that works better. So we're going to try that out today also. So yeah, we make a one-dimensional embedding for the bias and the embedding dimensional embeddings for users and items for their embeddings. So this is like the default stuff, and also the bias itself. So this is going to be 0 right now, but the model is going to try to force it to be the average rating. So now actually to making the model itself, well, we take the user IDs that are passed to the model, we take the item IDs that are passed to it, and then we fetch the embeddings for the users and the items and the biases. Okay? So once we have those, what we can do is first do the dot product of the embeddings. So that's what we do. We just do the dot product of layers. So it's user embedding and item embedding. And then on top of that, we add the bias. That is like the overall bias. Then the user bias and the item bias. And then this rating prediction is returned. So basically, we're just following the formula up here and not doing anything with the loss. And now, yeah, we're just going to instantiate the class, and TensorFlow is going to do the rest of the optimization for us because it has autograd, which is very nice, or the TensorFlow tape, or I don't remember how it's called, but basically it does everything for you. So yeah, we're going to have a matrix factorization model, say the number of users, items, embedding dimensions. We're going to have it 64, but you can try more also. The regularization parameters, yes. So here we're going to use the Adam optimizer to optimize. I'm going to use the legacy version because that is better for M1 max, but you can use the normal non-legacy one. The loss is going to be mean squared error, and the metric is going to be mean absolute error. Yeah, so let's actually run these cells. Yes, and then, yeah, we're going to train our model. So we're going to give it the ratings of the users encoded and anime encoded. So those are the IDs of the stuff. And then the Y is going to be the correct rating. So it's the rating that we're predicting. And we're going to train it for 10 epochs with the validation speed of 0.1 and the huge batch size. So let's see how it goes. It's going to be a little slow. 1 minute per each epoch. So as we can see in the beginning, the loss is huge. It's around 1,000. Does anybody know why it's around 1,000? Because that's very huge. Yes, Leonard.
Because we also have a huge batch size.
True, but isn't it averaged over the batch size?
Yeah, it should be. Right. Well, then because we're squaring.
But wouldn't it be like?
No, yeah, you can just square then.
Okay,
Embeddings are randomly generated at the beginning.
Yes, they are randomly generated, and so.
It needs to train the embeddings, so the initial losses will be quite high.
Yes. So basically, well, this is kind of an error from my side, but personally, you don't have. I don't think you have to fix that. But sometimes you get very huge losses, and that is because your model has the distribution rate of its outputs as very high. Because, for example, right now we have a bending dimension of 64, and which is filled with random numbers. And if you just add them all up, well, that's going to be a huge number. And you want to regress it to the number from 0 to 1. So you can imagine the difference in the beginning is going to be very high. So what the model is going to focus on is actually just get all of your values in the range from 0 to 1, rather than be training. And how you can combat this is just already think about how your losses are going to, or how your weights have to be initialized. So that is something you can do in here. My computer is dying. So that's something you can do in here. So embedding initializer, yes. So you can think about, okay, how do you want it to be? So you can have it random normal with a standard deviation, and then you can calculate the expected value of your vector when they're multiplied, and then you can already have it in the correct range. And if it's in the correct range, then it's going to be much faster in training. So that's a good tip for you also. Yeah, in the meantime, we already trained 7 epochs, and we have the mean absolute error of 0.3. Is that good? or 0.4? Oh, 3. No, why not?
It's definitely not good because we have values between 0 and 1. So even if we take these square root of that, it's still 1.5 off.
Yeah, so mean absolute error is the absolute difference, so you don't have to square root it.
Absolutely. Oh yeah. Then
So
it's even much worse.
exactly, it's very bad. And another way we can tell it's bad is because if we look at the baseline models we had, the mean absolute error for them was 0.1. So as you can see, the model that we're using with making with the stochastic gradient descent, it sucks. And what we can also do is plot the training and validation loss. Just use some Copilot magic. And yeah, let's see. Maybe our model is actually overfitting. Who knows? Yeah, one more epoch to go. It's 30 seconds now. Actually became much faster. Nice. So now if we plot the loss curves, that's interesting. Well, this is, as you can see, the huge loss from the fact that we had to first correct the domain range, the values range. But if we make the PLT limit for y, for example, from, let's say 0, 1, then we can see the loss curves, which is much better. So we can see the loss is definitely decreasing. It is converging at the epoch 10 already. But that's not good enough. That's very not good. If we look at the mean absolute error, that is also not good. But the model is converging, and it seems to train good, actually. So if you maybe train it for more epochs, then it's actually going to work. Let's also test it on the... Oh yeah, that's going to take a while. But let's test it on the test set. And yeah, I promise you it's not going to be better still. So we have to come up with something that trains better, trains faster, has a better score. What do you think it is? Well, what can we change so that it is better and faster? Hint from myself, it's something that was given in the previous lecture.
We are training how to
Does anyone know? It's all right. Let's look at the previous lecture slides in the meantime while it's training. Oh no. How is this possible? Is it slide? No, bruh. I'll have to fix that later. So last time we talked about alternating least squares or something like that, ALS basically. And well, it is shown that this algorithm is better apparently than the rest of the algorithms for especially matrix factorization. And that is something that we're doing right now. And let's just think about it. Why is it better? And yeah. So here are a few comparisons. So stochastic gradient descent, very flexible, can train anything, including this. can be parallelized. However, it's slow, doesn't converge fast, which we actually saw here right now. It's harder to handle unobserved entries. That is true. Just gonna have to believe that. ALS is reliant on least loss squares only. And that's exactly what we're doing here right now, right? Because, well, we're right now trying to find the difference of square ratings squared. So if we're going to use this, then that works. It can be parallelized. It converges faster than stochastic gradient descent and easier to handle unobserved entries. So that's awesome. That's exactly what we need. But what's the difference? The difference is in the way it is optimizing. So stochastic gradient descent tries to optimize U matrices, so the user matrix and the V matrix, which is for anime, at the same time in parallel. And if you think about it, that's like trying to hold 20 plates at the same time. So you try to balance all it out, and then you have to go to like another end of the earth or something. So that's a very hard task. But what's easier to do is you first take a batch of plates, you move them, you put them, and then you take another batch and you move it. Then you take all the batches again and you move them. And that is faster and easier. So that's kind of how to think about it. And also if you think about the ALS, that's actually just linear regression, literally. Because you know for linear regression there is a defined solution. Do you know that? Yeah. Because, well, you just run the formula and then it pops out. So what you can do is you can fix the U matrix. And you know that you have, do I have this formula? Yes. So you have basically something that you have to optimize for. So A equals U times V. So if the U is fixed, so that's, for example, the axis, and then the final matrix is A, and then you have to find the V matrix. That's easy to do because, well, that's literally linear regression. You can do some linear algebra and find the V, right? So now, technically, if you do the linear regression again and again and again, at some point, it is going to converge to something. And that something is the final like matrix factorization. So yeah, this thing should have completed to this point.
Does it only work with matrix factorization? Like it's just a method?
It's a specific method for doing matrix factorization, yes. So yeah, here we can see that matrix factorization using stochastic gradient descent does very poor. Only the mean absolute error is 0.2, which is actually better than on training, but still is worse than our baselines. So yeah, we're gonna use alternating least squares. And it's gonna be exactly the same model. So we're gonna have the user embeddings, you're gonna have the item embeddings, which we define here. However, when we actually do the custom fitting, we're gonna first fix some of the weights. So say that user embeddings is fixed, it's not trainable on even epochs. And then on odd epochs, the item matrix is not trainable. And then we're gonna train both of the matrices and see how that works. Yep. So as we can see, first of all, the loss is already very low. That is actually very nice. And the mean absolute error is, well, that is bad. Yeah. Similarly, we're going to also train it for 10 epochs and see how it goes. Yeah, that is going to take about 6 minutes. In the meantime, yeah, we can look at the algorithm, how it is coded. Does it make sense? So we have a for loop in the custom fit function, like basically 10 epochs, for example. Well, we fix some of the weights and then unfix the other weights, right? Then we just train it. And then we do it 10 times. Okay?
And what exactly is the difference now to what we had before?
Yes, so now the difference is that the user embedding and the item embedding are fixed at each epoch. So on
Yeah.
even epochs it's fixed, then on odd epochs it's not fixed, and so on.
Okay.
So it's the same task, but just one of them is fixed and one of them is not. And yeah, makes sense. And then here you just do linear regression. I'm doing stochastic gradient descent here because, well, our rating matrix is so huge that we cannot even do linear regression on it. So we're going to have to do stochastic gradient descent to actually train that.
And it is still a linear regression.
Yeah.
But we just cancel it algebraically.
Yes, we cannot do it directly, so we do it by using gradient. Yeah, so as we can see here already, our model right now is already better than the previous one on the third epoch. Imagine that, that's pretty cool. And on the fourth one, it is already surpassing the previous two baselines. And imagine what happens on the 10th epoch.
We get a perfect score.
Exactly.
So if we just draw a straight line here, it's obvious. Okay, if we disregard the fourth epoch, it's obvious that we're gonna get negative error, negative absolute error.
That is not possible.
Yes, we're in the virtual world.
True.
In the imaginative.
So, yeah, this is something that you can try, and I'm pretty sure this should be doable on the competition data set also. And yeah, let's give it another 3 minutes.
Can you explain again how you keep things? I'm lost.
The embeddings fixed.
Fixed, yes.
Yes.
Like how do you automate that?
Okay.
On the computer doesn't
So in TensorFlow, all of the layers have an attribute which is called trainable, as you can see here. So, for example, the user embedding is also a layer, which is the embedding layer. And if you put the trainable to false, then it's not trainable, so it's fixed. Yeah, that's it pretty much.
So it would be
And yeah, so let's run this part.
Have you ever worked on a machine that you logged into via SSH from another machine that you had logged into via SSH?
That's why would you do that? Why don't you log in through SSH in the first machine?
Because you can't log into via SSH into the second machine directly.
I see. Are you talking about Hubrock?
No, I'm talking about the Cognitron group. So, in
yes.
their office they have a PC,
Yeah.
right? And, well, it's on the Uni network, but to get into the Uni network I have to log into my Linux or into my Uni workspace, and then from there I can get in. But I can't get directly,
Well,
which is very weird.
You just do SSH twice. What's the problem?
That now when I do the second one, for some reason a lot of functionality doesn't work, like auto-completing tab, which is the most annoying thing ever. Or actually the only thing that I've noticed so far that doesn't work, but it's still. Oh yes, and I also can't go up through my history of commands.
Ah, yes.
Which both of those things.
That's sad. I cannot help you anything with. Okay, so the training has completed, and we can see the mean absolute error, at least on the training set, is 0.8, which is nice. It's 0.8. Oh, 0.9. Yeah, if you round it. And now we're gonna do the evaluation of the training set, and that's gonna take around 2 minutes. So as you can see, machine learning is a fun but also slow process.
You should be able to parallelize this. Right?
My MacBook is doing that, yes.
Oh, but it looks like it's not batching. Looks
Maybe
like
it is not. I don't. I would assume it is. It should, by default.
Can you look at your GPU?
Is there a batch? Oh, bro, I didn't put the batch set. Bro, I'm cringe. Okay.
You can rerun it. I think it's going to be much faster even now. So.
Should I rerun it?
Yeah. Good.
What? That's crazy.
Well.
Oh my god, thank you.
Okay.
So let's see. Oh, yay, it's also 0.9. And that is better than our previous models. So that's awesome. Now we can continue on to content-based filtering. Yay. So to be honest, I've never done content-based filtering before, and I'm just doing it off my intuition, like how would I program that. I've read a few papers, and that looks like, why would you even do that? So I'm gonna do it my way. And I'm sorry, this is not very useful, but maybe it is useful. So yeah. So kind of my intuition behind content-based filtering. So if you actually, let's say, have some vector embedding of your anime, and if you have, for example, like by genres, right? We saw that on the previous lecture. So where was it? Yeah, here we have it. So this is an example from the previous lecture, and we have some vector embedding. So for linear algebra multivariable calculus, this is like a binary vector, so it's a one-hot encoded. We have machine learning 1, easy homework 1, but the rest are zeros. And same goes for these guys. So how are we going to train our model? First of all, we're going to take all of the vectors that the user has liked, and then add them all up, and then subtract all of the vectors that the user has not liked, and add them all up, and then average all of this. And this will be our vector representation of user based on the training set. And I think that makes sense, because, well, if you have an average representation of what user likes and what he doesn't, then it should be like a, I don't know, point that is like the centroid of the cluster of whatever he likes. Makes sense, I guess. So that's what we're gonna do. Ideally, you would do it just by also multiplying the weight. So in the previous case, we have something like or not like. In this case, we have ratings, so we're gonna have to multiply ratings by the vectors. But I was too lazy to program that, so I'm gonna just gonna do not the weighted average, but just the normal average. So yeah, let's actually see how you implement this. So yeah, first of all, this is very inefficient. It's gonna take forever probably, but it works. So if we take the user as our person that we have to find the embeddings for, and then we have like a just fallback value as the user mean, then what we're gonna do is gonna do exactly the same thing. So we say that the user mean is the fallback value, we'll calculate it, and then for each user we're also gonna see what of the animes they liked. So that's gonna be the selection. If it's not 0, then we're gonna take the genres, so that's all the columns from number 4 to the end, because, well, if we look here in the anime stuff, these are the genres. So we're just gonna take the average vector that the user likes. And then we're gonna multiply that by the rest of the vectors and see what is the cosine similarity between them. Okay? Yeah, that's how we do prediction. So we have the embeddings from the users, we save them. Then in the training set, we just take the user embedding, anime embedding, multiply them, or just take the cosine similarity, and then save that as the prediction. That is gonna also return us values from 0 to 1. And yeah, so here we have the first part running, which is calculating the user embeddings. That is going to take 3 minutes. Yeah, in the lecture recording, it's going to be, I hopefully, going to speed it up. Does anyone have questions about this method?
Yeah, I tried running the code on Colab and it actually crashes at the matrix factorization part. It just runs automatically.
Really?
Yeah.
It's crazy. Is my MacBook that good?
It's also a MacBook in the Colab environment.
True, but on the Colab environment, yeah, maybe the RAM is small.
12 gigabytes.
Yeah.
Mine is 8.
But it's if you run out of RAM, it's just gonna buffer that onto the SSD, so it's gonna be slow. Yeah, but it's not gonna crash.
I see. Why doesn't that happen on Google Colab? Can you turn it on, maybe? Or, to be honest, I have no idea. I just run stuff and it works, and I'm happy with that. Living with pink glasses and everything.
You stopped in M1, yes?
Yes.
Is that right? Yeah.
Do you also have M1? Unfair advantage.
It is quite a nice machine.
True. Also, I heard a few complaints from the participants that the data is not loading into memory, but it takes 15 seconds for me. For them, it takes like 10 minutes. That's crazy. That's why I also broke it into the shards on Kaggle, because
Wait.
how it
can
helps.
10 minutes. Is your memory just completely full, and then it has to like always kind of find little
I don't know.
little empty spots?
How are they loading the data? To pandas or just some custom data code?
Oh, it's pandas probably. It should be pandas. But yeah, okay, so now training is done. Now we're doing predictions, and that's gonna take.
Can we batch predictions again?
Yes. Yeah, that's what I said here. Like it should be done within linear algebra, but I didn't want to think about that. But the problem here is kind of like you have this if-else statement, and I don't really know how to make it using linear algebra. Like.
Boolean mask?
But that's huge. Or not. Let's do some live coding. That's, I think, better spirit. Okay, so yeah, what I check for is if the user is in the embeddings. Well, in our code, of course, he will be, because that's how we defined everything. So user embeddings is a dictionary. That's kind of useless. We can make it more parallelizable using just make a huge matrix for the users.
Yeah.
And
Wait, but how many users do you have?
yeah, that's a lot.
I mean, it would be a very sparse matrix, right?
No, that's oh yeah, it kind of is actually. But that's fine because that's the embedding matrix of the users themselves. So it's going to be like number of users times the dimensionality of the vector.
No, okay. Yeah, no, yeah, you're right. You're right. That's completely fine then.
And what else we can do is, you know what? Yeah, that's the spirit, right?
Yes.
Okay, so make this code I don't think it will work actually. I have no idea how to spell parallel lines. No, bro, it's fine. What else? Should I add anything to it? Maybe batching.
Yeah.
Multiprocessing, bruh.
What?
No, we don't want to use multiprocessing.
Yeah, that's not parallelized. Then we
Cancel,
have to,
cancel, bro. First of all, let's switch to GPT 3.5. I don't have that much money. Or actually, let's use GPT 4. Batching and make it only using NumPy. Do not use multiprocess. Yeah, that's better. Yeah. That seems legit. Just copy this, replace it here, cancel, and then let's try again. I hope it does not crash. So it doesn't do the progress bar here though. This is smart. So it already makes the embeddings of the data frame. Then it saves them as values. Yeah, so previously the training was 3 minutes. Let's hope it is less than 3 minutes. And on the prediction it actually might die. So let's hope it's not gonna. Because that's quite a lot of stuff to predict. I think our test set was huge. Yeah. That's crazy. I could not even read the number. Oh, it's predicting. Oh, okay. Inhomogeneous part. Setting an array of the sequence. So, yeah, you're just gonna have to trust me it works. And it's not gonna be better than the previous models. Let's return it back. Another thing I wanted to show today is how to use BERT embeddings. And that is very cool. And so what we're gonna do is we're gonna do exactly the same thing, but instead of having just the genre as a vector, we're gonna have the BERT embedding as a vector. I'm gonna repeat that. But I think you know the drill. So this is some code I also wrote using Copilot or ChatGPT. Basically, it uses PyTorch to get us the BERT tokenizer, BERT model. For each text, we actually do it by batches. We, let's say batch sizes like 128.
How big are our texts? Is it just the genre?
No, it's this explanation of the, it's a synopsis.
Yeah, depends on your bird. You're using the base and paste. Yeah, 125. 128 should be easy.
Why is it 127?
Why does it take so long for...
Yeah, but the thing is, once we do it, we don't have to do it again. So we just save it as a NumPy file,
Yeah.
which I haven't done actually, unfortunately. So
I mean, it's gonna take like an hour.
yeah, but an hour is not that bad.
No.
Yeah. So let's assume we have done that, and let's see what we do next. Well, this code is actually exactly the same as the previous code, but instead of, oh, my computer is dying. Instead of using the genre embeddings, we're going to use the BERT embeddings, and then it, yeah, very slowly computes the predictions for all of the users. Okay? And yeah, I would love to actually run it and see how well it does, but unfortunately we do not have enough time. 1 hour is quite long. So I'm going to cancel this actually and say, yeah, this is basically how you do NLP in recommendation system. You make those vectors and then you average them. And I don't know, but I would assume it is decent. But the thing is, once you actually have those vectors and you have the embeddings and you actually make your predictions, what you will get is you'll get the predictions from the BERT model, you get the predictions from genres, predictions from ALS, right? And now you have like 3 files of predictions. And what you can do then is you can build a hybrid model. And that is what everyone does because, well, every model is good by itself, right? Because the ALS, it only uses the ratings that the user has given. BERT model uses a synopsis, so which text the user will like. And the genres model is going to use the genres, so which genres the user will like. So those are 3 types of different data. And then what you can do is you can take the average of those ratings that those models give, and that will be a hybrid model. And at least what I got in my previous time, so I've also been working on this anime recommendation systems data set. And my hybrid model was performing better in everything. Yeah.
Just by taking the average of the others?
Not really. So what I did is I took the weighted average. So I took the predictions from the rating model. I took the prediction from the interaction model. Because there's also interactions actually available in this data set. So how long this user has been watching this anime, how many episodes and stuff like that. So I built 2 models, interaction model and rating model.
Yeah.
And then you just do linear regression. So for the training set, what are the best lambda 1 and lambda 2 that balance out the weights in such a way that you get the best rating possible?
Lambda 1 and lambda 2 are just
Trainable parameters of linear regression.
scalars.
Yes. So J rating is basically a vector, right, of your predictions from one model. J interaction is a rating of predictions from another model. And then what you do is you give that to linear regression and say, okay, given the true ratings, using these 2 vectors, try to predict what is the rating matrix, and then you get these weights. Once you get these weights, you can use them to predict on the training set. And usually when you combine the models, when you build a hybrid model, or how it's called, an ensemble model, it performs better. It always performs better, and that's like what you see on Kaggle. On Kaggle, everyone who wins uses an ensemble model, which is a combination of multiple models with some very weird weights, but it works. On practice, I wouldn't do that, but for the competition, for the sake of the competition, it does a good job. Because, well, this is now overfitting technically. You're overfitting to the data set. For the competition, that's fine, right? But in practice, I wouldn't recommend doing that. Maybe you can do that. I don't know.
I mean, in the machine learning course, we were taught that we should use ensemble models.
Yeah, but ensemble models, they meant are different. They mean like gradient boosting, for example,
Oh yeah.
which is
Okay.
also an ensemble model, and you can technically. Oops. Gradient boosting, yes. Yeah, so gradient boosting is just a ensemble model of trees. So you have a tree, then you have another tree predicting the errors of the first tree, then you have another tree predicting the error of another tree, and then the loss just decreases magically. I have no idea how that works, but, well, no one actually has idea how that works. But yes, and if you actually want to use that, you can use sklearn. Also, by the way, you're not limited to actually using like neural networks. You can, for example, use gradient boosting on top of the bird features. You can use gradient boosting on top of the genres, and then that is going to work also. And that is technically going to be faster also than what we're doing right now because, well, neural networks are huge, they're deep, and it's going to take forever. Probably if you leave this overnight, it's going to run perfectly. Yeah. That's all I have for today. Thank you for watching. If you have any questions, feel free to ask, or maybe send me a message on WhatsApp or Gmail, because I send you the emails, right? So you can ask there. Yeah, that's it. Thank you for coming, and yeah. Yeah, also, by the way, next week we're going to have a lecture from Viaviate, which is a company that does vector databases. And that is not useful for the competition, but it's a very cool technology that you can use at work, for example, and that's a very nice skill to have. And vector databases are awesome because you can, for example, give memory to large language models. And that is not something that a lot of people can do, but if you know how to do it, I think that's quite valuable. Yeah.
Do you have a picture for this?
For VIV8 or for this event?
For this one.
No, I have only for the first lecture and last lecture. I'm sorry. Cover kind of is doesn't want to give 4 pixels for this event. It's too much. Yeah, I hope you did not just come for the pixel. Okay, thank you. Yeah. If you have questions, you have my email. You can ask there. Also, yeah, make a submission to the competition page, even if it's just a sample submission. Oh, nice. Recommend droids. Who is that? That's you, Leonard. Yeah, nice. Yeah. You can also try random. Maybe that's better.
Yeah, we will try.
All right. Thank you for watching, and see you next time on Monday. Bye.
Yeah.